Hello everyone, I am Tuhinur Rahman, lecturer of physics, Cambrian School and College. I hope you are all safe and sound. Welcome to today's physics class. Now, before starting my class, I'm going to show you some pictures. Let's try and get to this topic, okay? Now, in these four pictures, you can see in the first picture, this is a waterfall. In the second one, it's a roaring motion, and in the third one, this is a river going through the hills. And the fourth picture is a waterfall as well, but this is a relatively quiet one. And then next to photos or GIFs, the photos that I have used at the last, this is one of my most favorite photos regarding this topic. The person you see here, this is a scuba diving, you know this. The person is Guillermo Neri, and this is one of the most famous diving, scuba diving. And if you closely observe this photo in the middle, you can see that there are objects falling through a liquid or in gaseous substances. Now, from watching these pictures, can you guess what we are going to discuss today? Yes, today's topic is the flow of fluids and the viscosity. By the end of the lesson, you will be able to describe viscosity, explain Newton's law of viscosity, and last but not least, at the end of this lesson, you will be able to calculate the viscous force. But if you want to understand to this topic, the things that you need to understand first are fluids and its flow, viscous force, and the viscosity coefficient. Now, my first topic is the fluids, but before that I am going to discuss about the states of matter. You know this, okay, but just for the sake of it, you see this is a picture of a piece of rock. This is a solid object, and if we could go to the molecular structure, this would look like this. You know, this is a glass of water, this is liquid, and this is its molecular structure, and this is gaseous substance. There is another state of matter, you know that. We call it the plasma, okay, the ionized state. And two of the most common examples is when a lightning strikes on the free surface or the surface of a star. Now, in between these four substances, only two of them can flow. If you keep a solid in some place, it will stay there, and the plasma, it will not move. But if you keep a liquid or a gas, it will move from one point to another. Now, this is the liquid, and it's the molecular structure, and this is gas and its molecular structure. So from this point, we are going to properly define the fluids. You see, the materials that flow are called fluids. So the liquids and the gaseous substances are combinedly known as the fluid. Now, fluids flow in two ways. One of them is the streamline flow, and the other one is the turbulent flow. The first topic is the streamline flow. This is the waterfall, as I have shown you before, and if you could go to its molecular structure at the atomic level, you will see that during the flow of fluids, if all the particles follow the previous particle with the same velocity and they maintain some weight, then like this, and this is, if you consider or closely observe this photo, you will see that the particles that are in front are being followed by the particles that are behind it. So the definition of the streamline flow is during the flow of fluids, if all the particles follow the advanced particle moving with the front with the same velocity, then that type of flow is called the streamline flow. Okay. My next topic is the turbulent flow. If you consider this photo and its molecular structure, if you could show you that the particles, they are not maintaining any discipline, they are moving in a zigzag path. So this type of flow is the turbulent flow. Its molecular structure will look like this if you could take a picture or snap. And this waterfall, it shows the turbulent flow. Okay. So the definition of the turbulent flow is if the velocity of the particles of liquids randomly changes. As a result, they flow in a zigzag path and loses all disciplines, then this type of flow is called the turbulent flow. Now, I'm going to discuss a topic which is not very properly discussed in the SSC level, but those of you who want to do well in the admission test, especially in medical, and sometimes in the SSC level, in the MCQ question, it is frequently asked, but in the admission test, it is one of the most frequently asked questions. Okay, the Reynolds hypothesis. Professor Osborne Reynolds, he gave a hypothesis of how fluids flow. He said that there is a velocity that's called the critical velocity, which we are going to denote and define later as Vc, which means the critical velocity. He says the critical velocity of a liquid is directly proportional to the viscosity coefficient, which we denote by eta. And the critical velocity is inversely proportional to the radius of the tube. And the third one is the critical velocity is inversely proportional to the density of the fluid. Now, if we combine or join these three postulates or hypotheses, we can see, or we can write, Vc is directly proportional to eta division rho r. Now, if you want to remove this proportionality constant, we can write Vc equals Re eta divided by rho r, where Re is the Reynolds number. Using Reynolds number, we can say which type of flow the liquids are going to have. And the definition is the speed and direction in which the flow of liquid changes from streamlined to turbulent. Okay, that velocity is called the critical velocity. Now, using the Reynolds number, we are going to try and explain the flow of fluids. This is a vortex straight around a cylinder. It has a Reynolds number of 40 to 1000, and this is a very common thing in our daily lives. This is honey. It has a Reynolds number below 200. Now, if the Reynolds number is below 200, we can call that type of flow as the streamline flow. Okay, so when the Reynolds number is below 2000, we can say it as the streamline. The next one is, you can see this is an ocean. It's a rather calm one, and if you consider this photo, you can see that it's turning into a bit of turbulent. We're having some turbulence here. In that case, the Reynolds number, it varies from 2000 to 3000. So when the Reynolds number varies from 2000 to 3000, we can say that that type of flow is turning from streamline to turbulent. This is a very important topic. Okay. The next topic, you can see this is a waterfall, and you can clearly say that the fluids or the particles that are moving forward are turbulent. And there is another example. This is a rolling motion. In that case, we can see that the Reynolds number is more than 3000. So when the Reynolds number is more than 3000, we can call that type of flow as the turbulent flow. Okay. Now, my next topic, or my main topic today, is the viscosity. You see, you know resistance. You can define resistance. It's the impedance or the resistance is the impedance of flow of electricity during in a conductor. Viscosity can be compared to resistance. You can see when we are trying to drop an object through a liquid, you will see in this photo that all the objects are not falling at the same time. The first one is taking the highest time and the last one, or the bigger object, is taking the lowest time, because whenever an object tries to move through a liquid, it opposes the liquid. You can see the viscosity is the property of the liquid. This liquid opposes the relative velocity of the object, or in gaseous substances as well. So these are the photos of phenomena of viscosity. We can define as the property of fluid. What do you call the fluids? Liquid or gaseous substance. That means viscosity can be determined in gases and liquid substances. So the property of fluid, by virtue of which it opposes the relative motion between its different layers, is called viscosity. We are going to discuss about layers. Now, this is a sculpture of probably the greatest scientific mind who ever lived. Can you guess who this guy is? You see, this is a rather famous one. This is a drawing of Sir Isaac Newton, the left hand side, by Godfrey Kneller when he was 46 years old. So these two are photos of Sir Isaac Newton. Some might say that he was born in January the 4th, 1643, and he died in March 31, 1727. But in the Old Testament it says he was born in December the 25th in 1642 and he died in March 20 in 1726. Now, in your opinion, what is the greatest scientific book that was ever written? The greatest scientific book that was ever written is the Philosophia Naturalis Principia Mathematica. Now, I know it's not important in the SSC level, but this name of this book is going to be very necessary, and sometimes it's very frequently asked in medical admission test that when was the book, the Philosophia Naturalis Principia Mathematica, was published. If you closely observe it, you can see that the year given here is 1686, but when we are in the SSC level books, it's written as 1687. Okay, 1687 is the year when this famous book, probably the greatest scientific book ever published. Now, why I am going to discuss it? Why is this book here important? You see, in this book there were 3 chapters. In the first chapter, Sir Isaac Newton, he discussed about the force. The first chapter, you know this formula, F equals ma. You know that. He discussed that in this book in the first chapter. And in the second chapter, you know gravity and gravitation as F equals G capital M divided by R square. That's the law of gravity. And in the third chapter, he discussed about the flow of fluids. And he gave a formula of viscosity. So we are going to discuss about Sir Isaac Newton's law of the viscous force. Here you can see we took a glass of water and there is a marble or a spherical object, if you want to say. Now, if you drop it, you will see that that marble will feel some force and it will drag some layers of the liquid. That means some of the liquids will come to the lower part with the marble or the ball. Now let's just take its shape. We are going to properly discuss and define Sir Isaac Newton's law of viscosity. This is a fluid, and as a child you used to draw fluid levels as this. We are going to call it as levels. So let's consider this is the glass and if we draw the lines, these are the fluid layers. This is our layer 1 and this is the second layer, and we can take any other layers. From there we are going to try and say two things: the thickness of the layers, that means this distance is the thickness of the layers, and you can see when we drop an object through a liquid, at first the velocity increases and eventually it will decrease at some point it will be constant, which we are going to discuss in my next lecture, because in fluids it's going to be we are going to need Stokes theorem and the terminal velocity, which we are going to discuss in the next video. But in this video we are going to discuss about the fluid layers and this change of velocity. Now let's consider this is a layer, okay, first layer, and we can take other layers as well. These are our fluid layers. Now layer 1, layer 2, and you can name as many as you like. Now let's consider the area of the layer is A. You need to know one thing that's very important. The area when an object falls through a fluid or that means a liquid or a gas, the area of the object matters, because the bigger the object, the bigger the area it will pull with it. So let's consider this is our area, which is A, and the distance between two layers we are going to define it as dy, which is the thickness of the layers. You can take any other from this one to this one. All of them are dy, which is the thickness of the layers. Now, as I have said, at first the object will go through with the velocity, and velocity will increase. So we take the velocity at the first layer is v, and in the second layer is v plus dv. That means there will be some increase of velocity. Now the change of velocity, okay, the change of velocity is dv, because we need to subtract the velocity of the second layer to the first layer, so it's going to be dv. Now my main topic here, the main thing that I'm trying to discuss here is the velocity gradient. The velocity gradient is the change of velocity division the thickness of the layer. So here the velocity gradient is denoted by dv divided by dy, which is the change of velocity divided by thickness of the layers. Now the Newton's law, it says if there is a relative velocity between two layers of fluid, then the tangential viscous force that acts opposite to the flow, it's directly proportional to the area and the velocity gradient of the layers at constant temperature. This whole shenanigan, it must be done in a constant temperature. You do not want to change the temperature, because the viscous force will change, because the state of the matter will change. So you need to keep that at constant temperature. Okay. Now we are going to try and find out the mathematical formulation of Sir Isaac Newton's law. So the first one we can write is force is directly proportional to A when dv by dy, or the velocity gradient, is a constant. And the second one is F is directly proportional to the velocity gradient when A is constant. Now if we combine these two formulas, we can write as F is directly proportional to A dv by dy when all the quantities change. Now when we are going to remove a proportional sign, we take a constant, right? So we can take as F equals constant A dv by dy. So this constant is denoted by eta, which is the coefficient of viscosity. I'm going to discuss about the coefficient of viscosity, or the viscosity coefficient, because that's very, very important. Now, according to Newton's law, we can classify the fluids by Newton's law. This is a glass of water, right? And you know this is oil paint. Now, there is a fundamental difference between these two fluids. One of them obeys Newton's law of viscosity and the other one doesn't. So this is Newtonian fluids. What are Newtonian fluids? The fluids that obey Newton's law of viscosity is called Newtonian fluids, and the fluids that does not obey, the fluid that do not obey Newton's law of viscosity are called non-Newtonian fluids. Now, this is a very important MCQ in the SSC level or in admission test. It will say or ask, give an example of a non-Newtonian fluid. In your SSC level books, the only example that's given as in oil paint. Okay, so oil paint is a non-Newtonian fluid. Now, my next topic is coefficient of viscosity. Okay, I have written Newton's law as F equals eta A dV by dy. We want now, if we substitute the value of the area as 1 and the velocity gradient is taken as 1, we can write the formula as this, as F equals eta into 1 into 1. So it becomes F equals eta. From this point we want to define the viscosity coefficient. Okay, as you can see, the tangential force requires to maintain unit velocity gradient. The key part is we need to keep the value of dV by dy to 1. That means the velocity gradient must be 1. So the definition is the tangential force required to maintain unit velocity gradient. As you can see, I have highlighted it. Between two layers of fluid or liquid is called the coefficient of viscosity. It is denoted by eta. This whole thing must be done, or the experiment must be done at constant temperature. You do not want to change the temperature because it will change the viscous force of the viscosity coefficient. Now we are going to discuss about the effect of temperature on viscosity. So the first one is eta is directly proportional to root over T. That means temperature. Viscosity of gas. In case of gases, this relation says that if we increase the temperature, then the viscosity coefficient will increase, right? Because it's directly proportional. So in case of gases, the viscosity coefficient increases with increase of temperature. And in case of liquid, you see there are no formula or direct relation to how to determine, but there is one that's given as log eta equals A plus B by T, which says where A and B are constants and T is the temperature. As you can see, as T is inversely proportional in here, so we can fairly say that the viscosity of fluids, it's inversely proportional. That means if we increase, that means if the viscosity of liquid decreases with increase of temperature, that means if you increase the temperature T, then eta will change. It's, you see, this slide is very important for the SSC level student, and when you go beyond the SSC level for your admission test, it's going to be very necessary. Okay, it can be experimentally shown that if for water at 10 degrees centigrade, if the viscosity coefficient is eta and we take the water to 80 degrees centigrade, we can see it becomes 1/3. So if at 10 degrees centigrade it's eta, at 80 degrees centigrade the viscosity coefficient of water becomes 1/3 of eta. That means when we increase the temperature, the viscosity coefficient it decreases. Okay. Now effect of pressure on viscosity. There is no effect of pressure on viscosity of gas according to Maxwell's kinetic theory, which we are going to discuss about James Clerk Maxwell and his kinetic theory of gases in chapter 10. But there can be found some exceptions, such as in low pressure. Okay, and the viscosity of liquid increases with increase of pressure. If we increase the pressure on a liquid, it will eventually try to convert into solids, and you can see the solid has more viscous force or the viscosity than the liquid. They have gas is the lowest, liquid is the highest, but as I have said, viscosity is the property or quantity of fluids, which is liquids and gases. Now this is time for evaluation. Okay. Now, the first question is, determine the force required to drive a copper sheet of area 10 to the power minus 2 meter square horizontally with a velocity 3 into 10 to the power 2 meter per second through oil of thickness 2 into 10 to the power minus 3 meter. The coefficient of viscosity of oil is 1.55 Newton second per meter square. The coefficient of viscosity has a unit of Newton second per meter square or Pascal second of oils. Which I'm going to discuss about all the units and dimension in this chapter in my next lecture. Now, I have said in all my videos here, the key to solving mathematics regarding physics is that you need to find out the key information that are given in the STEM. You see, the force is given here, the force required. The question wants us to find out the force. Area is given as 10 to the power minus 2 meters square horizontally with the velocity is given and the thickness is given and the coefficient of viscosity is given. So we can write the formula as F equals eta dV by dy, where F is the force, eta is the viscosity, coefficient is the area, dV is the change of velocity and dy is the thickness. So here we write the initials as area is given 1 to 10 to the power minus 2 meters square. Velocity is given as dV equals 3 into 10 to the power minus 2 meter per second, and the thickness, this is dy, equals 2 into 10 to the power minus 3 meter. The viscosity coefficient is given as eta equals 1.55 into 10 to 1.55 Newton second per meter square. The question wants us to find out the viscous force, which is F equals what? So it's a relatively easy math if you understand. If we substitute all the values, the force becomes 2.325 into 10 to the power minus 1. That's the answer. Now, I have kept two questions for you to practice. Okay. First one is, a metal sheet of area 0.01 meter square is placed on a glycerin layer of 2 millimeter thickness. Okay. I have highlighted the keywords here so that it's easier for you to solve. If the required horizontal force is 0.4 Newton to drive the metal sheet with 0.05 meter per second velocity, then the question wants us to determine the coefficient of viscosity. I think if you understand this topic or watch my lecture with a bit concentration, I think you will be able to answer this question, solve the problem. Now, the next question is, determine the force required to drive a metal sheet of area 2 into 10 to the power minus 2 meters square horizontally with a velocity 4.5 into 10 to the power minus 2 meter per second through oil of thickness 1.5 into 10 to the power minus 3 meter. The coefficient of viscosity of the oil is 2 Newton second per meter square. I think the keywords here are marked. Now, usually I do not like to state some things about scientist or statement, but here I am going to say something about Sir Isaac Newton. You can see Alexander Pope, he said, nature and nature's law lay hid in light. God said, let Newton be, and all was light. He was probably the greatest scientific mind who ever lived. I hope you have enjoyed my class today. That's all.